When we're thinking about how to prove different types of theorems throughout this class, it will help to have formalized some basic rules for logic operations, and we'll do that with Boolean algebra. Boolean algebra, like any other type of algebra, involves the manipulation of variables, but the variables that we'll be manipulating are Boolean variables, meaning that they can only take on the values true and false, or equivalently 1 and 0. And for those of you who have programmed in a typed programming language like C or Java, you can think of Boolean as a type of variable like int or float, except that the set of possible values for Booleans is just true and false. And we can manipulate Boolean variables using logic operators, and we can define those logic operators in terms of their truth tables. The not operator applies to a single statement, like the variable p, and flips its truth value. So if p is true, not p is false, and if p is false, not p is true. The AND operator applies to two statements, like the variables p and q, and the AND of p and q is true when both of the variables are individually true, and it is false otherwise. So in building these truth tables, we are exhaustively enumerating all of the possible truth values that the variables in the expression could jointly have. Since we have one variable here, the total possibilities for the truth value are that that one variable can either be true or false. When we have two variables, we have 4 total possibilities for their values, because the variables could be both true, or the first true and the second false, and so on. So in a truth table, we will have a row for every possible combination of truth values for all of the variables. And so then the number of rows in the truth table doubles every time we add another variable. And you can think of these truth tables as defining what the operator does. This would be similar to defining what does plus do by listing for every possible pair of integers what is the result when you add that pair together. That's obviously infeasible for the set of integers, but here, since our set of possible values that the variables in the expression could take on is small, we can actually exhaustively list for every combination of inputs what is the output. The OR of two Boolean expressions evaluates to true if either or both of the expressions is individually true, and only evaluates to false in the case where both of the individual expressions are false. It's worth noting that this logic definition of OR is different from the way that OR is sometimes used as a word in everyday English, where when we say something like, I'll go to the store or to the movie tomorrow, we mean that one or the other, but not both of the two things could happen. So logical OR is sometimes referred to as inclusive OR to emphasize that it is also true in the case where both of the inputs are true, and to distinguish it from exclusive OR, which would be true only if one or the other was true, but not both. We've already seen truth tables for if-then and if and only if, but I'll write them again for completeness. Now that we have Boolean variables and a set of logic operators, and we know how the operators apply to those Boolean variables, we can think about 4 different logical expressions made up of Boolean variables and logic operators. What is their meaning? Something we might particularly look for between different Boolean expressions is, do those different expressions have the same logical meaning, which we express with the idea of logical equivalence, that 2 expressions will evaluate the same way for any possible combination of truth values of their variables. Let's make that more concrete with an example. In these 2 statements, if it rains tomorrow, then I'll bring an umbrella, and either it doesn't rain tomorrow or I'll bring an umbrella, we can identify the same propositions. It will rain tomorrow, and I will bring an umbrella. And in the second statement, the rains tomorrow proposition is negated. So if we write these as Boolean expressions, where P is it rains tomorrow and Q is I'll bring an umbrella, the first one would be P implies Q, and the second one would be not P or Q. And so to see if these 2 statements are logically equivalent, we can compare their truth values for all possible values of their variables, and we do that by writing down a truth table. Since I'm comparing multiple expressions, I've added columns in my truth table for each of the expressions that I'm going to be comparing. And since one of the expressions involves multiple logic operators, I've broken it down so that we can first figure out not P and then combine that into not P or Q. Not P should flip all of the truth values from the P column. And now for not P or Q, we need to look at these 2 columns and figure out where is it the case that either of the 2 sub-expressions, or both, evaluate to true. Here we have one of them evaluating to true. Here they're both false, so the or is false. Here they're both true, and here one of them is true. So those are both true. And for P implies Q, we look at the first 2 columns, and those are in our usual order, so we get the usual table for implication. And now we can compare the possible truth values for these 2 expressions across all of the rows, which compares across all possible combinations of values for the variables, and we see that they always have the same truth value for the overall expression, which means that these 2 expressions are logically equivalent. So we can use truth tables to build up the evaluation of a complicated expression by first evaluating the sub-expressions, and we can use truth tables to compare different expressions and sometimes determine that they are logically equivalent. And this leads us to our next proof template, which is an instance of exactly what we have just done. So our proof template for proving that two Boolean expressions are logically equivalent involves constructing a truth table and then verifying that both expressions always give the same result. And the example that we just went through is an instance of exactly this proof template. With the idea of logical equivalence, when we know that two expressions are identical in all cases, that means we can substitute one for the other, and that allows us to do algebraic manipulations on our Boolean expressions. And so it's worth listing out a bunch of these logical equivalences so that we know what sorts of manipulations are valid on our Boolean expressions. All of these equivalences are listed in Theorem 7.2 in the textbook. The commutative rule says that for both and expressions and or expressions, we can flip the order of the variables and they have the same meaning. The associative rule says that we can re-parenthesize if we have a sequence of ands or if we have a sequence of ors. Of note, this does not mean that we can re-parenthesize if we have sequences of mixed ands and ors. You can think of this as analogous to how addition is associative, so you can move the parentheses around if you have a bunch of additions, and multiplication is associative. But if you have a mix of addition operations and multiplication operations, moving the parentheses around can very much change the meaning. The identity expressions are saying that if we know one side of an and is true, or if we know one side of an or is false, then we know the result. And double negation gets us back the variable we started with. Anding a variable with itself, or oring a variable with itself, each give us back the same value as the original variable. The distributive rule looks a little bit like multiplication distributing over addition, in that when we take P and the expression Q or R, we end up with P and distributed onto both the Q and the R, and the two are ORed together. But there isn't the asymmetric relationship that we have between plus and times, because P or Q and R also distributes in the same way. And De Morgan's law looks a little bit like a distributive property, where the negation is distributing over an and or an or, but note that the sign is getting flipped. When we move the negation inside for an and, we get an or, and when we move the negation inside for an or, we get an and. All of these rules can be proven according to our proof template 4 by building a truth table. So let's take a look at just a couple of examples. To prove this identity rule, we can construct a two-row truth table because there's only one variable, which can be true or false. And the expression false is always false. And so now the OR of these two is true, and for both being false gives us false. And comparing P or false against P shows us that they are identical in every row of the truth table, so these two expressions are logically equivalent. And that means anytime we see an expression of the form, a variable or a thing that we know is false, we can simplify that expression to be just the variable. Now let's take on a tougher example, one of the distributive rules. And here we have expressions with 3 variables, and so that means that we're going to need an 8-row truth table. To make sure that my table lists all possible joint values for all 3 of the variables, I'll make the first variable have a block of trues, then a block of falses. Then the next variable I'll have blocks of half the size alternating, and then half the size again for the next variable until we get to the last column where we'll alternate true and false on every row. So now we should figure out some of these sub-expressions. So Q or R will definitely be helpful. The OR of Q and R will be true in all of the rows except for the ones where both of these are false. So we have true, 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 false, true, 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 false. And now we could AND that with P to get the left-hand side of our rule. So the AND will be true in the cases where both sides are true and false in all of the other cases. So we get true, 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 false, 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 false. Now moving to the other side of the expression, we'll need a column for P and Q, and we'll need a column for P and R. And again, for the AND to be true, we need both variables to be true. So P and Q are both true only in the first 2 rows. After that, Q is false or P is false. Then P and R will be true in the first row and the 3rd row, but false in all of the other cases. And now we have all of the sub-expressions we need to evaluate the whole right-hand side. And so here we get a true when either or both of these columns come out true. And so that happens in the top 3 rows. And then for the bottom 5 rows, we get false in both columns. I apologize that my rows got a bit off kilter, but we can now compare the columns for the left-hand side and the right-hand side of our expression. And we see that they both have 3 trues followed by 5 falses. So they have the same truth value for every row, and therefore we know that they are equivalent Boolean expressions. And so when doing Boolean algebra, we can substitute one for the other if that helps us. We could do similar truth table proofs of all of these logic rules, but I'm not going to go through that now. I will leave some of it as an exercise for you to work on during class. I almost forgot a couple of definitions we should go through quickly before the end of the lecture. Tautologies and contradictions are Boolean expressions that don't carry much meaning about the actual propositions within them, because just based on the structure of the logic operations, they're either always true or always false. For an example of tautologies and contradictions, let's look at a slight variation on our repetition rule from earlier. A variable ANDed with its negation is a contradiction because one or the other must be false, and so the AND will always be false, whereas a variable ORed with its negation is a tautology because one or the other must be true, and so the OR will always evaluate to true.